And I can bounce this tennis ball. I can throw it down. And let us assume, just for simplicity, that it hits the floor at about 5 meters per second, and that it's a very, very good tennis ball, and that it also bounces back with a velocity of about 5 meters per second. I will choose this to be my increasing value of x, and so it hits the floor like this. That means the velocity at which it hits the floor is minus 5 meters per second. It bounces off, and there it comes, and it goes up with plus 5 meters per second. I call this v1, and I call this v2. So what now is the average acceleration? Well, I would have to know the time that it takes for this change in direction. In other words, we call that the impact time. I would say in this case, the impact time delta t is probably about 100th of a second. And so my average acceleration would be v2 minus v1, that is plus 5 minus minus 5, that is 10, divided by 10 to the minus 2, and that is plus 1,000 meters per second squared. I have observed carefully the signs. If now I say, aha, I don't like this, I want to call this the value of increasing x. No big deal. This will become a plus, this will become a minus, and then this would become a minus. So then the acceleration is minus 1,000 meters per second squared. I have also here a tomato, and I have here some eggs. Now, imagine now that I throw the tomato down, or for that matter, the egg, and that they hit the floor at 5 meters per second. I could do that. They would not come back up. They would go pfft. So therefore, the change in velocity would not be 10, apart from the sign that you have to think about, but it would only be 5 meters per second. The impact time would probably be much longer, maybe a quarter of a second. So therefore, the average acceleration during the impact would then be only 5 divided by 1/4 would be something like 20 meters per second square. Now, whether you call it plus or whether you call it minus 20 meters per second square depends on your convention of what you call increasing x. But the eggs and the tomatoes don't care what you call minus and what you call plus. Whether the acceleration is minus 20 meters per second square or plus 20 meters per second square, you better believe it, the egg will break. So it's only in your convention that it matters, but of course the physics will not change. The eggs couldn't care less what you have chosen for your sign convention. Something breaks because the magnitude of acceleration becomes too high. That's why something breaks. A few days ago, I saw a Sherlock Holmes movie. And there was a guy who fell on the floor, a marble floor. Hit his head, was lying there motionless. And he was Watson. And Watson said to Sherlock Holmes, "What happened?" Sherlock Holmes walks over to the guy, touches him, and he says, he crushed his skull. He looked very intelligent, I must say, when he said that. He crushed his skull. And I said, gee, that's really physics in action. It's 801 all the way. A really modest velocity when he hits the floor. But he hit the floor like a billiard ball. The guy was bald, for one thing. And so the impact time was very short. And when the impact time is short, even if you hit the floor with a modest speed, the acceleration is high, and that was too much. And so that's why his skull was crushed. So what matters is this change in velocity and the impact time. We now want to make one last step from average acceleration. We want to go to the acceleration at any moment in time, just the way we did that with velocity. And that now is a natural step. The acceleration at any moment in time would be the limit for delta t goes to 0 for v measured at t plus delta t minus vt divided by delta t. So that is the instantaneous acceleration. And this, you will recognize, is the first derivative of velocity versus time, which is also the second derivative of position versus time. And so here comes the second equation that I really want you to remember forever and ever and ever, that the acceleration is dv dt, which is also d2x dt squared. We can go to our plot and we can ask ourselves the question now, where is the acceleration 0? Where is it larger than 0? And where is it smaller than 0? Because this value can be larger than 0, equal to 0, and smaller than 0. And now you have to be very careful when you try to derive that from this plot. You have to be very careful, because you and I have no good feeling for second derivative. Velocity is easy. All you have to do is looking at alpha. But when it comes to the second derivative, you have to see how alpha is changing. Well, right here, the velocity is not changing. So the acceleration everywhere here must be 0. Here the velocity is increasing. So the acceleration must be larger than 0 here. Here, the velocity is almost constant. It's almost a straight line. What does that mean for the acceleration? 0. Exactly. Here, when it makes this rounding curve, the velocity is positive here, but on this side it's negative. So what does that mean for the acceleration? Negative. You got it. And so you can now roughly find where the acceleration is positive, where it's negative, and where it is 0. Let's do a straightforward example, the way that you could expect it on an assignment, or if you are extraordinarily lucky, you might even get something like that on an exam. Very straightforward. I'm going to give you the position x as a function of time, and then ask you lots of questions about it. So this example is a working example. X equals 8 minus 6t plus t squared. So this tells you where the object is at any moment in time. And let this be in meters. What now is the velocity at any moment in time? Well, that's the derivative, dx dt. And I use the following: x equals t to the power n. Then, as most of you should know, dx dt is then n times t to the power n minus 1. That's all I'm using. So the derivative of 8 is 0. I get here minus 6. I get here plus 2t. This would be in meters per second. And the acceleration, I have to take the derivative of the velocity. I get plus 2. So notice that the acceleration is constant in time. It's not changing, but the velocity is changing. Well, at time t equals 0, I'll start to probe a little bit. I want to get a feeling for what this object is doing. At time t equals 0, x is plus 8. The velocity is minus 6 meters per second, and the acceleration equals plus 2. I can also ask myself, at what time is x equals 0? What are the times that x is 0? Well, I have to solve this second order equation, which is something that you've all done in high school, and you will find that that's the case when the time is plus 2 and when the time is plus 4. Take the plus 2, that makes this 4. 4 plus 8 is 12, minus 6 times 2, that's 0. So you see the 2 works, and you check that the 4 also works. just for my